Okay, in this investigation, we're going to go over some of the relationships that exist between circles and tangents, which we have studied before, and something real life called eclipses, which you also know something about, I'm sure. And what I'm going to start off with is some definitions of tangent lines, for example, in the circles. Then we're going to talk about some of the definitions that have to do with eclipses. And then I'm going to ask you a question to see if you can actually do the actual investigation itself, okay? So, this is actually in line with Common Core for high school geometry, circles, standard A4. Okay, so let's get to what an eclipse is. Now, we know that an eclipse occurs when, here's the sun. So let me just describe this real quickly. So this circle represents the sun, this circle represents the earth, and this circle represents the moon. And an eclipse occurs when the sunlight, which is shining on the earth and the moon, when the sunlight is blocked by the earth onto the moon when it's in this particular position, or when the moon is on this side. So the moon is between the earth and the sun, okay, and it casts a shadow on the earth. Now we're going to be talking particularly about when the sunlight is blocked from the earth, from the sun rather, blocked by the earth, so that you have a lunar eclipse, okay? Now let's talk about some of these lines that I drew here. You remember that tangent lines are lines that intersect the circle at only one spot, and they form 90-degree angles. And that's what this particular box is for, okay? Sorry about the focus taking place here. So they take place at a 90-degree angle, so that you see there's slightly different ones here. Now the tangent line that touches both the sun circle and the earth circle on the outside, but does not, see that, doesn't intersect on the outside line, this is called an external tangent. And I'll explain why a little bit more here in just a second. Just like this particular tangent line right here on the outside, okay, is also called an external tangent. Now, the characteristic that you need to know about external tangents is that they will intersect, but outside the two circles. Okay, so for example, the two external tangents, as you see as they continue, intersect right there. Okay, now in opposite, it would be the internal tangents. Now let's talk about what the internal tangents are. There's one right here. Again, it has a tangent line right here. But this one actually goes to the opposite side of the circle, as did this particular tangent line right here. The characteristic that you want to be aware of that internal tangents, and let me just finish labeling here. Internal tangents intersect in between the two circles. Okay, so that's the most important characteristic of those two. Now, so you'll notice that we have an intersection here for the internal tangents. We have an intersection here for the external tangents. Let's talk a little bit more about this particular diagram, okay? Now, this diagram is deceptive. We know, for example, that the diameter of the sun, remember that the diameter just goes straight across the center point. The diameter of the sun is actually approximately 880,000 miles. Now, that's pretty big, okay? The diameter of the Earth, on the other hand, is approximately 8,000 miles. Now, the way they're drawn here, it looks like maybe, 4 or 5 of these diameters of the Earth could fit across the diameter of the sun, but that's just not true. 880,000 divided by 8,000 is about 110. All right, so basically 110 of these circles should fit across the diameter of whatever proportionally sized sun there is. Well, that would make it pretty darn big, right? So again, if we're going to scale and assume that this is the size of the Earth, we'd want 10 of these. So let me see, 1, 2, 3, 4, 5, 6, 7, 8. So approximately out to there. Okay, let's just say that's actually 10. We need 11 sets of that size to be the diameter of the sun, which you could see would just go off the page and it'd be really pretty huge. Okay. Now the other, and that kind of gives it these tangent lines a different perspective, doesn't it? The other thing that's slightly off about this particular diagram is that the distance between the sun and the Earth is 93 million miles. Okay, which means that and again, considering the size of the sun, that means that these tangent lines are going to be a lot more angled than what you can see here, right? Now, in contrast, the distance between the Earth and the Moon is 280,000 miles. Again, so this looks like, the approximate distance to here, is maybe, I don't know, 20 or 30 of these could fit in between. But the reality is 11,000 diameters of the sun, of the moon, of the Earth rather, fit in the distance of 93 million miles. So again, these are things that are really, really far away. Now, the question that I want you to investigate, and you don't have to actually arrive at a number. If you do, bonus points for you. But I want you to see if you can figure out. Oh, actually, I'm sorry. There's a couple more definitions I wanted to go over. Now, again, you'll notice that these tangent lines kind of represent the sunlight from the Earth, from the sun rather, that's covering the Earth, and then this area right in here represents the shadow. Let me just go ahead and do that. Let me draw this up. So this area in here represents the shadow that's cast by the Earth, okay? And it actually forms somewhat of a triangular shape, doesn't it? That particular area that's all in orange here, that's actually called the umbra. U-M-B-R-A. And when the moon is inside the umbra, it's completely darkened, okay? Now, the area that's just outside here, these other two little triangular areas, okay? Actually, let me just do a more contrasting color so you can get a better idea of it. There we go. This area that I'm actually outlining in green is called the penumbra. P-U-P-E-N umbra. Sorry if that's going off there. Penumbra. And that's where partial eclipses actually takes place. So when the moon is actually into here, you can see partial eclipse. So again, the questions I want you to try to investigate is this. You'll notice that this is almost a triangular shape, right? Can you estimate the area from the center of the Earth all the way to the tip of where these external lines, let me just make this a little bit bigger here. There we go. Can you estimate the distance between the center of the Earth and the tip of this triangular umbra area? All right. Also, can you calculate the area of that triangular shape that is the umbra? All right. That's the investigation. If you can't get actual numbers, if you can just tell me what the procedure you would need to know and maybe pieces of information that you don't have and that you would need to know, that would be helpful. That would be great. Okay, so that's your investigation. Good luck with it.